Swayam Prabha. Digital India. Educated India.
Welcome everyone to this first session in this series of video lectures on this course Introduction to Aerodynamics. As some of you are aware of, this course is a core course offered to undergrads in aerospace engineering, and they take this course in their third semester. Although it is a core course for aerospace engineering students, we see that from time to time students from mechanical engineering, physics and mathematics also sign up for this course. And as you go through this course, you will see the reasons for that. Aerodynamics has a lot of facets that can engage people from different backgrounds, and I hope, since it is an introductory course, we will be able to when we cover the wide range of aerodynamic phenomena, the spectrum of aerodynamic phenomena, you will get to see that there is a lot of things from physics, mathematics, chemistry, even geometry that comes into the subject matter. Now, this semester is going to be online. So, for those who are following this course on TV or over the internet online, you can, if you have a question, you can reach out to me. You can send me an email. You can find my email from the institute's the department's web page. I will try to respond as many as I can. Before I begin this presentation, I would like to draw your attention to the picture that I have included here. This is the picture of a SR-71 Blackbird, and it is considered to be one of the hallmarks of aeronautical design. I want you to look at this picture and make a mental note of what comes to your mind when you see a picture of an airplane like this at this point in time. And then again, when we are finishing up with the course at the end of the semester, I want you to look at this picture once again and see how that mental note at the end of the semester compares with the mental note that you make at this point, when we are starting off. I think some of you, I know that there are enthusiasts who know a lot about these things, sometimes more than what many of us know. But for those of you who are having a gradual introduction to aerodynamics, I think this exercise will show you the utility of a course like this, Introduction to Aerodynamics. So, we are not focusing on any particular aspect of aerodynamics, and that is sometimes the beauty of a course like this. That is, aerodynamic phenomena, there are a lot of aerodynamic phenomena that occur at various flight speeds, various circumstances. When you go into follow-up courses in aerodynamics, such as low speed aerodynamics, high speed aerodynamics or hypersonics, there your focus will be on a narrow band of flight Mach numbers, and you would go into detail of the analytical details of phenomena occurring within those Mach number windows. But here, since it is an introductory course, we have a little bit more freedom to move around the Mach number line. Of course, I have not talked about what is Mach number at this point, but you will see that when we study aerodynamics, there will be some of these non-dimensional parameters that will occur all the time, and I would expect that you at least get familiar with these with these numbers. So, we have Mach number, which essentially is the ratio of the speed of the object or the speed of the flow divided by the speed of sound, and you understand the speed of sound has to be the local speed of sound. So, if you are trying to calculate the Mach number of an aircraft flying at say 30,000 feet, you have to find the velocity of the vehicle and divide it by the local speed of sound, and you will get the Mach number at which the vehicle is flying at. Now, the importance of Mach number will become clear, and it will be like a central theme around which a course like this will be organized, and in fact, the entirety of aerodynamics is arranged around that Mach number line. Okay. So, we will talk about what is Mach number, but what I mean to say is a course like this, we can go from very low Mach numbers to very high Mach numbers, because it is an introductory course. We can touch upon a lot of topics and a lot of things happening at these different Mach numbers. And the intent of this whole process is that when you go into these more courses such as high speed aerodynamics, where you are looking at really Mach 1 to Mach 5, you will feel at home. So, at least you will have some physical insight or phenomenological understanding of processes occurring in that band of Mach numbers, and there of course you will go into lot more details of the physical phenomena happening in that band of Mach numbers. Whereas, in this introductory course we will not go into as much detail as in those courses. You understand that the focus of this course is really on the breadth of the material rather than the depth of it, but nonetheless we will still have some fundamental topics of discussion, such as because a lot of you do not have background in fluid mechanics, and a little bit of fluid mechanics is necessary to appreciate the phenomena that are happening around these objects flying through air, or when air is moving through a channel or a duct. You will see that there are differences between external aerodynamics, internal aerodynamics that stem from these kind of arrangements. But nonetheless, I hope that by the time you go and take the subsequent courses in aerodynamics, this course will prepare you to have an intuitive feel of the physical processes. Okay, so before I talk about anything, I think it is a good point in time to introduce the textbooks that I would recommend for this semester, for this course. Introduction to Flight by John Anderson is a book that anyone in aerospace engineering should go through once. This book has a very nice coverage of aerodynamics, structures, flight mechanics and propulsion. So, it gives you a broad coverage of the different verticals that are important in aerospace engineering. Okay, so, you understand that aerodynamics is one of those verticals, but we also have propulsion, we also have structures, we also have flight mechanics. And for those who want to become experts in aerodynamics, knowledge of these other fields, structures, flight mechanics, etc., is essential. In fact, propulsion and aerodynamics have a lot of overlap, and sometimes a big chunk of propulsion systems deals with internal aerodynamics, and there are courses such as gas dynamics of propulsion. You can find on NPTEL there is a course on gas dynamics of propulsion. So, essentially gas dynamics is almost something synonymous for aerodynamics with some small nuances, but nonetheless Introduction to Flight is a book that all of you should read at least once from end to end. And this book is not only focusing on aerodynamics, but it is focusing on the different verticals that are important in the design of aerospace vehicles. And in many cases aerodynamics has to integrate with propulsion system, aerodynamics has to integrate with the structures, aerodynamics of course influences flight mechanics, the performance of vehicles, the stability and controllability of vehicles. So, it is important at this point to read this book for having that kind of grasp of the overall material. In terms of aerodynamics itself, Fundamentals of Aerodynamics is the book for this course. Fundamentals of Aerodynamics again has a very nice coverage of the material, starting from the low speed to supersonic Mach numbers, and I think this book will be sufficient for this particular coursework, Introduction to Aerodynamics. But again I would like you to go through this book again like in detail, that is, do not just rely on the material that I am presenting in this course, in this lecture videos, because the way I think about it is what I am presenting is really a way to help you read these books on your own. Okay. So, my lectures are really supplementary material, so that when you read these books you might have some questions in your mind. My courses are just, my lectures are supposed to help you in your self study of these two books, okay, 1 and 2. Now, for the further courses in aerodynamics that you have in subsequent semesters, there are some more books that I would recommend you guys to at least take a look at the content of these books. Okay. Modern Compressible Flow with Historical Perspective, again by John Anderson. I have this bias for Professor Anderson, not because I was one of his students back in my grad school at the University of Maryland, but you will see that a lot of aerospace professionals they hold Professor Anderson in very high regard for the textbooks that he has contributed to the aerospace community. In fact, Professor Anderson I think has about 6-7 books that are again benchmark textbooks in different topics in primarily aerodynamics, but again the Introduction to Flight is also by John Anderson. Then he also has a book on computational fluid dynamics. So, Professor Anderson's coverage of aerodynamics and the peripheral subjects is immense, and the books are written in a very lucid storytelling way. So, very good for self study. So, this book Modern Compressible Flow, you see that the word aerodynamics does not appear here. Instead, we have this expression called compressible flow, and you will see that when we discuss. So, I already indicated that there is something called Mach number, and that is defined as U by A, where A is the speed of sound. Now, remember that when as aerodynamicists, when we talk about the speed of sound, what we really mean is the speed at which mechanical disturbances, small amplitude, small perturbation mechanical disturbances, say fluctuations in velocity, fluctuations in pressure, etc., are moving. So, you have the velocity of the flow with respect to the body of interest, or the velocity of the body with respect to the flow of interest. So, essentially the relative velocity, and then you divide it by A, which although we say is the speed of sound, but essentially what you are trying to say is velocity, relative velocity of the object with respect to the flow divided by the speed at which small amplitude perturbations in pressure, velocity, etc., are moving around in the vicinity of where you are measuring u. Okay. So, this A, which is the speed of sound, you have to calculate it. So, I should say it is the local speed of sound. Okay. So, if you have an aircraft that is flying at 32,000 feet at a given velocity, say Mach number of the aircraft, we often abbreviate as like this, would be the velocity of the aircraft divided by the local speed of sound. So, what does local speed of sound mean here? The local speed means you have to go to that altitude, find the temperature, because you will see that the speed of sound or the speed at which these small perturbations in velocity and pressure, etc., move around is related to the local temperature. So, A for most of our applications will be given by square root of gamma RT. So, you have to find the local temperature, and you know that temperature varies significantly with altitude. Okay. There is something called the standard atmosphere, is available in the form of charts and also in the form of graphs. From that standard atmosphere chart or table, you have to look up what is your temperature at that altitude 32,000 feet in this example, and then you have to calculate the speed at which small perturbations in pressure, velocity, etc., move around at that altitude, and then you can calculate the Mach number of the aircraft based on this ratio. Now, why we do this? Why instead of the velocity we talk about Mach number will be introduced in one of our subsequent lectures, but at this point keep in mind that if you are really concerned about the time your suppose you are an airline operator and you are concerned about how much time will it take for your aircraft to travel from say Calcutta or Kolkata to New Delhi. So, the distance is approximately 1500 kilometers, and if your vehicle is flying at some speed, now what speed are you talking about, right? In this case, the operator will be focusing on ground speed, that is the ground distance is 1500 kilometers. So, what is the ground speed will give you the time when you will reach at Delhi if you leave at Kolkata at a certain point in time. But when you talk about aerodynamic phenomena, you will see that Mach number is something that becomes relevant, that is at what Mach number will the flow transition start showing small shock waves on the vehicle surface, at what Mach number the flow starts becoming compressible. So, the behavior of fluid do not your operator is interested in some aspects, interested in the time from A to B. So, he is using the ground speed and the distance between A and B, whereas the fluid mechanical behavior around the aircraft as it is moving through atmosphere, we see that different characteristic phenomena start showing up at different Mach numbers. So, here ground speed is not important. So, you have ground speed, then while the aircraft is flying you can have headwind, tailwind, etc. So, the relative velocity of the aircraft with respect to the surrounding air can be different from the ground speed, and then when you calculate the Mach number based on that relative speed, you will see that aerodynamic phenomena start somehow mapping to different bands of Mach number, okay? Not to the ground speed, not to the relative speed either. So, it depends on the relative speed of the vehicle with respect to the surrounding air, but it also depends on the velocity at which these acoustic perturbations move in the vicinity of the aircraft. Okay. So, essentially you need to know the temperature, that will give you the speed at which these disturbances propagate, and why fluid mechanical behavior depends on that ratio is something that we will consider in subsequent lectures. But at this point just note that this Mach number range, so at different Mach number ranges different fluid mechanical behavior or aerodynamical behavior starts showing up. So, I have a slide that details that, but at this point I want to at least mention, because there is no harm in repeating a few important things, that is if you draw a Mach number line like this starting with m0, here I make a demarcation for m1. So, what is m1? m1, so Mach number is 1 when? Mach number is 1, u by a is 1, u by a is 1, this implies u is equal to a, that is your vehicle is flying at a speed which is equal to the local speed of sound. Okay, that is, so for example, the modern commercial aircrafts, Indigo, SpiceJet, they fly maybe 0.8 Mach, close to that range. SR-71 that I showed in the first slide can fly at, can cruise at Mach greater than Mach 3. So, greater than the speed of sound. So, SR-71 can travel, so that 3 times faster than 3 times the speed of sound, I think translates to something around more than 3500 kilometers per hour. So, the distance from Kolkata to New Delhi is 1500 kilometers, and the velocity of this aircraft SR-71 at cruise can reach 3500 kilometers per hour. So, you can work out the math for the time it will take from Kolkata to New Delhi. Okay, so again keep in mind that there are other issues with running supersonic aircrafts between crowded cities. So, it is introduction to aerodynamics. So, we can introduce all these things. So, if you have crowded cities, you will run into problem of sonic booms and the problem of aeroacoustic noise. Sonic boom is essentially for supersonic aircrafts, you have shock waves and these shock waves, when the vehicle is flying close to the ground, the shock waves can actually impinge on the ground, and where these shock waves pass across, for example, it can shatter the glass of the windows, etc. So, it is often a major challenge to have supersonic airliners to land in airports in crowded cities. And also there is the question of engine noise. So, it is not just the sonic booms, but noise comes from some aeroacoustics behavior. For people who are interested in, you can look up Lighthill's equation, and you will see that sound can be generated due to some fluctuations in aerodynamic variables. But nonetheless, introductory course, so I am at liberty to talk about these things, but again these things are advanced topics, but you can look it up on Wikipedia if you are curious. So, Mach number 1 is essentially where your vehicle is flying at the local speed of sound, and then there is this special Mach number 5. Around Mach number 1 we have this small band. Now, this band, there is nothing so precise about it, but typically we say that, say, from 0.8 to 1.2 Mach number, something special happens, because of which this window is known as the transonic Mach number. Transonic, okay, so across sonic, you can see that 0.8 to 1.2, less than sonic, a little more than sonic. So, that is the transonic window. Some important behavior happens in that corridor, we will see that. Now, this line left of Mach 1 is of course subsonic, less than sonic. The line on the right hand side is greater than Mach 1, so that is supersonic, and beyond 5 we have hypersonic, and we will I have a slide that talks about what happens in these Mach number corridors. But I brought up all this discussion to really explain the name of the textbooks, that is why instead of just aerodynamics we are calling this compressible flow. It is seen that above Mach number 0.3 your flow of the gases or air, if you want to just stick to air, although it is subsonic, it starts exhibiting compressible behavior. We will talk about what this thing means in a subsequent slide. Compressible behavior. What is compressible behavior? Something that can be compressed by the application of pressure. Okay. So, we will see what is so special about Mach number of 0.3, that below it the flow behaves incompressible. So, below Mach number 0.3 flow is subsonic, of course, because it is Mach number 0.3 less than 1, but on top of that flow is also incompressible. Incompressible means that your density in that flow field is neither changing with time nor changing with space. So, density is constant for this flow field, incompressible. And more precisely, density is not sensitive to change in pressure, because we will see these things in a subsequent discussion. So, do not think that this is all that I am going to talk about this, why it is incompressible, but it is good to introduce these things, so that when we come to the detailed coverage, you will already be having some idea about, or at least some information that you can work with. So, incompressible behavior essentially means that that 1 by rho d rho dp, okay, the fractional change in density due to change in pressure is negligible. So, compressibility is defined as, so if you consider this is your specific volume, So, volume per unit mass. And of course, we will see that compressibility, when you calculate compressibility, it depends on the method in which you measure compressibility. So, here my subscript T stands for isothermal. So, I am measuring compressibility. So, you have a vessel where you are maintaining the temperature constant, and then you are applying or increasing the pressure on the vessel, and you are trying to see what is the fractional change in specific volume. That will give you a measure of the compressibility of that particular gas, and that will be called isothermal compressibility. Similarly, you can also have something known as isentropic compressibility. We will talk about these things. These things really is the first chapter in compressible flow or high speed aerodynamics, but nonetheless, since this is an introductory course, again we are at liberty to talk about almost everything that occurs in aerodynamics. So, isentropic means, just think of it as you are running an experiment. So, you have a vessel that has a V, it has a lid on top, and you are pressing on the lid, increasing the pressure in the vessel, and you are measuring what is the change in specific volume, because you have started with unit mass, but you are doing the experiment in an isentropic manner. We will talk about what is isentropic, but at this point you can just think of isentropic as something that is adiabatic, that is, there is no heat transfer in or out of the system, and also there is no dissipation. So, for example, there is no friction. So, if there is a combination of no heat transfer and no friction, you can consider some of these experimental processes as isentropic. So, nonetheless, so you can calculate the compressibility of a fluid, but the problem is in a flow situation, you are not talking about a piston cylinder experimental setup in a flow situation, right. In a flow situation, how do you see the change in the specific volume? By the way, if you replace specific volume, now V is nothing but 1 by rho, because V is specific volume. Okay. So, V can be written as 1 by rho, where rho is density, and in that case you will see that these compressibility expressions become 1 by rho d rho dP at constant. So, just you replace the V by rho and drop the negative sign. Similarly, here also it becomes 1 by rho but the problem is, okay, at this point do not think that again that this is all the discussion about these things we are going to have. We will spend enough time on discussing what is compressibility of a fluid and what is compressibility of a flow. Now, these are two slightly different things. A fluid can be compressible, but it may not exhibit compressible behavior in a flow, okay? And a fluid can be compressible and it can exhibit compressible behavior in a flow. And what we are saying here is, if a fluid is compressible above Mach number of 0.3, it will exhibit compressibility behavior. We will talk about it in the subsequent lecture. So, you understand then that modern compressible flow with historical perspective essentially deals with Mach numbers in the compressible range. So, above Mach number 0.3, and a large portion is really dealing with supersonic flow fields. Okay. So, this book is a textbook for high speed aerodynamics. So, when you go into your third year, you will have a course on high speed aerodynamics, and this book is a prescribed textbook for that course, because this book focuses on the different aspects of supersonic flow. When you have supersonic flow, the compressibility behavior becomes quite dominant, and you have the occurrence of shock waves. We have shock waves. Shock waves, as we will cover in one of our lectures, shock waves are discontinuities. In a flow field, it occurs only in supersonic flow fields, and we we will see why that is so. Across these shock waves, flow properties change suddenly. It is like a step function. So, you have a shock wave, your flow here has a certain temperature. The moment you cross the shock wave, your flow temperature increases like a step, and the increase in the temperature depends on the strength of the shock wave, and we will see that the strength of a shock wave depends on the free stream Mach number upstream of the shock wave. So, there are all these different things that we will be talking about, but the modern compressible flow with historical perspective essentially covers compressible flow in the supersonic window of Mach numbers. After that, I have given the name of elements of gas dynamics by Lippmann-Roscoe. Elements of gas dynamics by Lippmann and Roscoe. Now, this one is a classic text in aerodynamics. When I say classic text, what I mean is a lot of other books and material are often a rehash of the material in Lippmann and Roscoe. It's actually a very thin book compared to a lot of other books, but elements of gas dynamics, also you see that instead of aerodynamics, here we the authors have used the word gas dynamics, and you will see that aerodynamics, gas dynamics, then you have aerothermodynamics, that is when you go into like the compressibility effects kick in. So, above Mach number 0.3, you will see that thermodynamics enters into the picture. For example, here already you see that we talk about temperature, we talk about entropy. So, these are thermodynamic comes from thermodynamic considerations. So, when you talk about the compressible behavior flow, so Mach number 0.3 and above, or if you have a book that focuses on supersonic flow, you are really talking about aerodynamics with merged into thermodynamics. So, sometimes authors like to give the name gas dynamics, where some thermodynamics is also creeping into aerodynamics. Okay. And in this additional reading material, the last one is Hypersonic and High Temperature Gas Dynamics by John Anderson again. This book, as if you see this number line, if you go above Mach 5, it is still supersonic. Anything above Mach 1 is supersonic. But what happens is, as we keep on increasing the flow, either the flow speed or the vehicle speed with respect to the flow. So, say we are holding, so we are moving at a certain altitude. So, our temperature is fixed, so velocity of sound is fixed, or velocity of small amplitude mechanical disturbances is fixed, and your vehicle is flying at a certain speed, and we are gradually increasing that speed. So, what will happen is your U by A ratio will start increasing, because your A is constant, because the height we have kept fixed. So, you will first hit say Mach 1, Mach 2, Mach 3, and you see that okay, the shock wave angles are gradually decreasing and things are changing, but around this Mach 5. So, Mach 5 is not a very tight water boundary, but around Mach 5 sometimes it can be Mach 4.5, sometimes it can be Mach 5.5, sometimes it can be as late as Mach 6, but some very distinct aerodynamic phenomena start showing up. So, it is still supersonic flow, but on top of that supersonic consideration, there are some very interesting phenomena that starts happening once you cross Mach number 5ish, and so this region is given the name hypersonic aerodynamics. This book, the Hypersonic and High Temperature Gas Dynamics by John Anderson, goes into detail of these kind of flow fields, and we will in one of our future lectures touch upon why or what are these special things that happen in hypersonic flow fields. For those of you who are really interested in aerodynamics, who see and when I say aerodynamics, even high speed propulsion systems and propulsion systems by themselves involve a lot of aerodynamics. So, if you are interested in aerodynamics or propulsion, I would recommend that you also take a look at, I mean it is not always possible to read all these books right now, but at least you should be aware of what are the good books Of course, there are lot more than this, but again I have to limit myself at some point. So, I have two books that I have I am recommending as even more reading materials. So, the Dynamics and Thermodynamics of Compressible Fluid Flow by Escher Shapiro. Now, this is again another classic book, and the Principles of Ideal Fluid Aerodynamics by Krishnamurthy Karamchetty. So, these Elements of Gas Dynamics by Lippmann Roscoe, this book by Shapiro and the book by Karamchetty, I consider them as the classic textbooks, and you will see that by the way, these Principles of Ideal Fluid Aerodynamics is something I think it is more amenable for these incompressible, inviscid kind of flow fields, but Karamchetty goes at length into talking about what is circulation, what is vorticity, what is the Prandtl lifting line theory. So, it has very good discussion in the segment where we are interested to find the lift and drag, the induced drag on wings and wing cross sections. Okay. So, Karamchetty's book is good from that viewpoint, but if you think of high speed aerodynamics and compressible behavior, thermodynamics coming into aerodynamics, then it is Elements of Gas Dynamics and the Dynamics and Thermodynamics of Compressible Fluid Flow. Now, I think it was around 2003 or 4 when I was in grad school, when someone pointed out to me that there was this set of wonderful videos on fluid mechanical phenomena, where some of the stalwarts in fluid mechanics and aerodynamics are showing experiments and explaining some of the fundamental behavior of fluids. And when I say fluids, it includes both liquids and gases. Okay. So, some of these people are showing experiments with liquids, some are showing experiments with gases, but in about 25 or 30 videos by some of the stalwarts in fluid dynamics, very beautiful demonstrations, experimental demonstrations of fluid mechanical processes have been documented. So, I will urge all of you, I will actually strongly urge all of you to go into these the link that I have there on the screen at mit.edu. So, these are the series of 30 video lectures that contain experimental demonstration. Say for example, there are videos on vorticity, circulation, the deformation of a fluid element, how vorticity is connected to the angular motion of fluid elements that deform while rotating. It is not a very simple thing to understand by looking at static pictures in textbooks and by, of course, just by going through the text. So, I think there are about 2 or 3 videos on vorticity by Professor Shapiro himself, and you will understand the value of these videos once you watch them. Now, if you search National Committee of Fluid Mechanics films on YouTube, you will get all the videos, but I still would recommend you to go to the link that I have given here to get the high resolution version, because on YouTube you have many people who have uploaded these videos. So, it is better to just go to the source from where everyone has picked up their videos. So, just go to this link, there are about 30 videos. Do not wait for me to discuss those topics. Go ahead and start familiarizing yourself with the physical phenomena, because remember, our focus in this course is to introduce you to the wide array of physical phenomena, of course, under the umbrella of aerodynamics. So, aerodynamic phenomena you can say, and watching these 30 videos. So, there is a very good series of videos on the physics of drag, and you will see that when we design aerospace vehicles, or rather aircrafts that move through atmosphere, drag becomes a very important consideration. So, when you move through air, there are various reasons why you need to spend power. So, your engine has to fight against, sometimes it has to fight against gravity, sometimes it has to fight against the drag, sometimes it has to, it depends on the orientation or the heading of the vehicle or the flight path. But nonetheless, you will see that this drag is a big problem. In fact, there is often this question that is asked, what is a wing? What is the wing? You see the wing on an aircraft. So, if someone asks you the question, what is a wing? You might tend to answer that these are the two structures on both sides of an aircraft, but technically anything, any object, any body which when properly oriented with oncoming stream of air produces lift that is considerably greater than drag can be considered a wing. Okay. So, that is from Karam Chetty. So, Karam Chetty's book gives you all these nice insights into these kind of things. So, it is not just a streamlined shape of the aircraft wing that you generally see. Of course, that is what satisfies this requirement, that any object. So, for example, this piece of paper, if I place it at a suitable orientation with respect to a relative wind, since this guy is not moving at all. So, whatever wind direction is coming is the relative wind for this. So, if I place it at a certain orientation, if the amount of lift, now what is lift? Of course, you understand lift is a kind of force that helps you to fly or helps you to fight gravity or helps you to stay afloat, some of those things I think would come to your mind, but we will have a more technical definition, so that we can avoid ambiguity. A purpose of definition is so that we all are on the same ground when we talk about physical aspects of things. So, is this a wing? The answer is okay, if you can orient it with respect to this relative wind, and if you can show that the amount of lift is considerably greater than the amount of drag, then of course, this can be defined as a wing. Now, the lift force has to be lot more than drag for this to qualify as a wing, and so you need to understand how lift is generated. Okay. So, the initial part of this course we will talk about the generation of lift, then we will talk about the generation of drag, and if you watch these series of videos, Professor, I think that is Shapiro as well, because Shapiro is the one in aerodynamics and compressible flow, etc. So, a lot of topics of interest for us, Professor Shapiro is actually demonstrating in these videos. So, this problem of drag is beautifully explained in this series of videos. Okay. So, watch it. What we will do is we will look at lift in a very overviewish manner in the beginning. We will go into drag of an airfoil or drag of a object, and we will go into detail of the drag, because I have seen that there can be two approaches in teaching a course like this. Okay. I start with the fundamental aspects of fluid mechanics. So, I start with explaining what is streamline, streak line, path line. Okay. A part of the reason why I talk about these keywords, even before I have discussed these things at any level, is some of you can go and look it up. Nowadays, access to information has become really easy, and YouTube and Wikipedia have some beautiful videos in fluid mechanics and aerodynamics, and aerodynamics is, or fluid mechanics is, a very photogenic subject, and a lot of flow field visualizations are there on YouTube. So, when I say something, you might like to do it as an exercise, look it up if there is an experiment explaining that on YouTube or somewhere else. Now, this drag, so okay, so there are some instructors who would start with the fundamentals of fluid mechanics. Okay, start with streamline, streak line, path line, then talk about what is vorticity, what is rotational flow, what is irrotational flow, what is circulation, what is the relationship between vorticity and circulation, what is the relationship between circulation and lift, what is fluid deformation, how do you measure the deformation of a fluid element, Then how do we define the rotation of a fluid element, because see in a solid body, when a solid body rotates, any pair of mutually perpendicular lines, both of them rotate by the same angle. In case of a package of fluid, when it rotates, it can also deform. So, then a pair of lines that was perpendicular to each other before the rotation, after the rotation may not be perpendicular to each other. So, if you try to define rotation of a fluid element in the same way you are defining rotation for a solid element, it will not be a very apple to apple comparison. So, if I started with the fundamental aspects of fluid mechanics or aerodynamics, so I would talk about all these things, but what I have seen is it is better to introduce at least one physical phenomena in detail, because if we talk about drag itself, you will see that we are covering a lot of physical processes. So, by the time we talk about vorticity, circulation, etc., you will have some idea of what physical process these topics fit in, instead of starting with those at the outset. Okay. So, what I will do is I will go into a detailed discussion of drag, and when I say drag, essentially we will talk about drag on a wing. You will see that when we discuss wings, we go into the discussion of a 2D wing. So, essentially just the airfoil. We will talk about what is a 2D wing or a and what is a finite wing. So, there is some difference between infinite wing or 2D wing, a finite wing. And once we do drag in a slightly thorough manner, we will then have the opportunity to go into some of the fundamental aspects of fluid flow. So, and also derive some of the governing equations. So, you will see that in fluid mechanics we have governing equations that connect the variables of interest. What are the variables of interest in aerodynamics or fluid mechanics? I mean, I think all of you can at least guess that velocity, density, pressure, viscosity, etc., can be our variables of interest. And what governing equation does is it helps you with some kind of a connection between these variables. Okay, a governing equation connects variables in fluid mechanics or aerodynamics as well, because aerodynamics is nothing but a subset of fluid mechanics. Governing equations essentially mean we will see that we have continuity equation, momentum equation, and energy equation. In an inviscid flow field, we have not talked about what is inviscid versus viscid, but at this point just let us suffice by saying that in an inviscid flow field the effects of viscosity is not present. Now, we cannot say that the fluid is without any viscosity. I mean, of course, hypothetically you have this thing called real fluids where viscosity mu is 0, but in most cases fluid does not have a viscosity 0. All fluids have some viscosity mu. Now, or the coefficient of viscosity. Now, what happens is the coefficient of viscosity or the viscosity by itself does not enter the picture unless there is a velocity gradient or unless there is a suitable velocity gradient. So, you need both a viscous flow and a velocity gradient for viscosity to manifest. So, if either your viscosity is 0 or your gradient is 0 of velocity, you can consider the flow field to be inviscid. In fact, we will see that when you look at flow over a body or flow through a duct and you zoom into the flow near the wall, that is where viscous effects are dominant. If you go away from the object into the free stream, you will see that the gradients of velocity are not such that the effects of viscosity will be felt. So, then the flow around the body at a slight distance away from the wall of this body can be considered to be inviscid. So, we will see that governing equations for inviscid flow, the momentum equation for inviscid flow is given a special name, it is known as the Euler's equation. On the other hand, momentum equation where viscosity is considered for the viscid case, we have the special name called Navier-Stokes equation. And we will, I am introducing all these words again, so that you can look them up, but we will go into details of all of this. So, long story short, 2 textbooks, some additional reading materials. You now know what is, why some textbooks call themselves as the compressible flow instead of aerodynamics, and some call them as textbooks of gas dynamics. And if you have interest in aerodynamics beyond your course curriculum, then you can at least take a look at these more reading materials. But watching the videos is a must if you want to enjoy this course. Aerodynamics is a very fascinating subject. The amount of physical phenomena that happen in aerodynamics it is not just flow over a wing or the flow over a fuselage. For example, there is something called gas dynamic lasers. That is, you take a gas, you heat it up, of course, you have to take the right combination of gases, you heat it up and you expand it through a supersonic nozzle with a very high expansion ratio, and what happens is you have this high energy laser radiation that is coming out in the divergent section. That is also an aerodynamic phenomena. Okay. So, recently India tested the high speed technology demonstration vehicle. This is powered by a scramjet engine. The vehicle flies in such a high Mach number. I am not exactly sure of what Mach number that is, but you can think of a hypersonic vehicle flying at Mach number 6 or above. The flow in the engine is also supersonic. Now, this is unprecedented. Generally, flow in the engine is reduced to subsonic speeds or even to stagnation conditions, but in a scramjet engine, we will not get into the details of all these things, but because it's the happening aerodynamics right now. So, I still need to talk about it. In a scramjet engine that powers these hypersonic vehicles flying at Mach 6 plus, the flow in the engine is still supersonic, and to ignite, add fuel, get thrust is a big challenge. That is also under the purview of aerodynamics. Of course, some chemistry, some thermodynamics is also there. So, we sometimes give it the special name aerothermodynamics, but nonetheless aerodynamics plays an important role there. So, starting from aircrafts, wings, the lift on wings, the drag on wings, the control surfaces, how they affect changes in angle of attack and stuff, how do you change the heading of an aircraft. So, we will talk about these things, but keep in mind that aerodynamics is not just the motion of an aircraft. Okay. So, we will have enough opportunity to look at those things. Now, to draw your sometimes I have seen that when I show a list of books, it does not create enough impact in the student's mind, and sometimes it is difficult to even remember the list of textbooks. So, that is why I go at a little bit of length at discussing the names and what kind of content we have in these books. But here I have put the pictures of these books. So, these are the textbooks that were listed in the previous slide. So, this one is, I think you can read this, but still this one is the Introduction to Flight, which I said is a must read for anyone who is trying to get into aerospace engineering, because this has a broad coverage. Then Fundamentals of Aerodynamics is the prescribed textbook for this course. Now, you know why we call this compressible flow to some extent. I mean, I am it is not justified that I just talk for 5 minutes and I accept you to understand what is compressible flow, but nonetheless this is compressible flow book. This is that classic book by Lippmann Roscoe. It is a thin book, but you will see that some very important topics covered in this book. Then Professor Anderson's book again on hypersonic and high temperature gas dynamics. So, for students who are interested in hypersonic vehicles, scramjet engines, re-entry vehicles. So, if you are interested in that range of aerodynamics, then this is the book for you, Hypersonic and High Temperature Gas Dynamics. This one is another classic book by H.R. Shapiro's book on compressible fluid. So, this both of them are compressible flow textbooks. Shock waves, shock interactions, shock boundary layer interactions, a lot of good discussions on those topics. And then you have these principles of ideal fluid aerodynamics. This is the book by Karam Chetty, and this one again has something that you might be able to relate between the aerodynamics, because discussions on lift and drag and Prandtl lifting line theory and a lot of fundamentals of aerodynamics. Okay, this book is very good in terms of those fundamental aspects of aerodynamics. Again, like the fundamental aspects of fluid mechanics as well, curl, like why the curl of the velocity field gives you vorticity, how circulation relates to vorticity, how circulation relates to lift. Those things are nicely considered in these books. Also, while we talk about the how airfoils are designed, you will see that there is something called conformal mapping and something known as the Zhukovsky transformation. It is a little mathematically involved, but Karam Chetty's book gives you a nice insight into that kind of transformation. So, we will end up this introductory session at this point. So, in this lecture we have talked about, we have made the introduction, I have shown you the picture of the SR71 Blackbird, and I have asked you to make a mental note of what comes to your mind at this point and then compare it with what comes to your mind at the end of the semester when you see the same picture again. Just to get you started with the process, this SR71 is one of the hallmarks of aerodynamic design, but the shape of the vehicle that you see is not guided just by aerodynamics. Since it is a reconnaissance aircraft, it is also guided by radar cross section minimization requirements. Okay. So, this aircraft is a spy plane or reconnaissance aircraft. So, it needs to have as little radar cross section as possible to prevent detection. The engines that you see on the two sides are actually a combination of two engines. It is a turbojet engine and a ramjet engine. At high speeds, the ramjet mode would kick in, at comparatively low speeds the turbojet would kick in, and so you can look this up on Wikipedia, and I think you will get some insight into the aerodynamic design of these vehicles. We talked about the textbooks and the specific reasons why they have been named so, and I hope you can find some of these books from libraries and some of them are actually now quite affordable because they have, I think, some Indian edition.